Hello friends, so today we are going to solve the questions, and the questions are from the year 2000 and from the year 2001. So from 2000 we are having 7 questions, as well as from 2001 we are also having 7 questions. In totality there are 14 questions. So in the first question, which was asked in the year 2000, and it states that a point source light S placed at a distance L in front of a center of a plane mirror of width D hangs vertically on the wall. A man walks in front of the mirror along a line parallel to the mirror at a distance 2L from it as shown. The greatest distance over which he can see the image of the light source in the mirror is. So we are given this figure. So we have light source S at a distance L from the mirror, and mirror is hung vertically, whose width is given as D. Man is walking in this direction at a distance 2L, and we have to see maximum distance at which he can see the image. So obviously the image of this light source will be only seen through the light that is being reflected from the mirror. And we can draw an approximate figure for it. So let us suppose this is our mirror, and we have a light source somewhere here, okay, and man is walking along this path in upward direction, and this is the mirror to us. And this light source is right at the center of this, because this distance is given as L, and the distance between the mirror and the man is given as 2L. So this will be also our L. So, and it is also mentioned that this source S is in the middle of the mirror. So we can approximately draw an axis of this mirror, which will be something like this. And so if we draw a parallel lines to the end of the mirror, so this distance will be also D. So obviously this distance will be our D by 2. And in order to see the image of the, you can say, the mirror, we can just draw its reflection from the edge of the mirror, and so this way and this way, and the reflection will be going this direction and other will be in this direction, so somewhere here. And if we converge behind the mirror, so they are going to form a virtual image somewhere here. Let us suppose this quantity is P, and we know in case of the mirror the distance of the object as well as image will be at the same distance. So we are going to get that this will be also our L. So our rays will be traveling this direction, and let us name these points. Let us call this as, this is our S, this is P, this century let us suppose is our O, we have this as M, N, and we can call this as A, B, C, D and E. So if we consider the triangles, our POM and triangle MBA, triangle POM and triangle we have MBA. And this triangle will be nothing but similar to each other. These triangles are similar, and because of similarity their sides can be written in ratio. So we can write our AB ratio MB will be equal to MO ratio PO. And let us suppose this MB is our Y. So not MB but AB is Y. So our AB is our Y and our MB is our 2L, and we have our MO. MO is our D by 2 and our PO is equal to our L. So we substitute these and we get this as Y upon 2L will be equal to D by 2 upon L, and this gives us that Y is equal to D. And from the symmetry we can easily write that our AE will be equal to summation of this AB is Y. Similarly we can say our this DE will be also equal to Y. So total length AE will be equal to Y plus D by 2, or rather we can say D plus Y. So we can say that our AE will be equal to, we can write this as AB plus BD plus DE. AB plus BD and plus DE. So AB is our Y, BD is our D, and DE also Y. And we just found out that our Y, this will be equal to our 2Y plus D, which comes as, because Y is already equal to D, so this comes as 3D. So we get that AE is equal to our 3D. So this is the, you can say, maximum distance which was asked for it. So we get option number D is the correct option. Option D is correct. We come to the next question. It was also asked in the year 2000, and it states that a rectangular glass slab ABCD of refractive index N1 is immersed in the water of refractive index N2, where N1 is greater than N2. A ray of light is incident at the surface AB of the slab as shown. The maximum value of angle of incident A max, sorry, it had to be alpha max, not A max. This is alpha max, such that the ray comes out only from the other surface CD is given by. So this question is based on the, you can say, total internal reflection. We want that ray should not pass through this AD surface but should be coming out from this DC surface, and this will be only possible if the total internal reflection takes place at the surface of AD. So we can draw a rough approximate figure for that. So this is our A, B, C and D, and we have a ray of light which is incident. Let us suppose this point is our P, and the refractive index of N1, so this is our N1, and other one is given as N2. Okay. So it is surrounded by water, immersed in water. Yeah. So it will be bending towards the normal. It will be going something like this, and for total internal reflection we want that it should be coming from this DC surface, so traveling in this direction. So let us call this as our R1, this our as R2, and this is our P. Let us call this as Q, and this point as our R, and we want this to be alpha max. So we can write that ray comes out of CD after refraction at AB, after refraction at AB, after refraction at AB gets totally internal reflected, gets total internal reflection at AD. Okay. And therefore we can write that our in triangle we have this is PQR, angle R1 plus angle R2 will be equal to 90 degree. Okay. And from here we can write that our R1 is equal to 90 minus R2, and we want that our R1 should be maximum. So we can write that our R1, if maximum, then obviously R2 has to be minimum. So it is 90 minus R2, and this will be our minimum. Okay. And for total internal reflection, we can write that for total internal reflection, the minimum R2 should be equal to the critical angle, that is theta c. This is our critical angle. And for critical angle, that is our theta c, we already know the formula that sine of theta c will be equal to n2 by n1. Or we can write that our theta c will be equal to sine inverse of n2 by n1. We already know that our R1 max is equal to 90 minus R2 minimum. Okay. So we can easily substitute it, and we can write that our R1 max is equal to 90 minus theta c, and theta c is our, so let me write this as equation 1. And if we use Snell's law at the surface AB or point P, Snell's law at point P, or we can say at the face AB. So we can write this as our N1 upon N2 will be equal to So we get this as sine of R1 max, sorry. Wait 1 second. N1 is, okay, N1 is inside. Okay. So we can write this as so you can write that our N1 multiply by sine of R1 max is equal to N2 and sine of alpha max. So therefore, we can find out the ratio. The ratio will be equal to our N1 upon N2 is equal to, this comes as sine of alpha max divided by sine of R1 max, and R1 we already know is our theta minus C. So this comes as sine of alpha max divided by sine of 90 minus theta C, according to equation number 1. And this gives us that it will be equal to, so N1 upon N2 will be equal to sine of alpha max and cos of our theta C. So we can now easily sort it out. So this will be giving us sine of alpha max is equal to N1 upon N2 cos of theta C. Therefore, our alpha max will be equal to sine inverse of ny by n2 and cos of theta c, and theta c is our sine inverse of n2 by n1. So we substitute it here, we get our alpha max is equal to sine inverse of n1 by n2 cos of, we have it as sine inverse n2 by n1. So this is the maximum value of our alpha, so that the ray comes through the opposite surface, that is our DC. Okay. So option number A is the correct one. Option A is correct. Next question. It was also asked in the year 2000, and it states that a diverging beam of light from a point source S having a divergence angle alpha, sorry, it has to be also alpha, fall symmetrically on a glass slab as shown. The angles of incidence of two extreme rays are equal. If the thickness of the glass slab is T and its refractive index is N, then the divergence angle of the emergent beam will be. So this is more or less, you can say, we can draw it by using, or we can find out the divergence angle of the emergent ray more or less by drawing the ray diagram. And for that, and we have a source somewhere here, and it is given that it is incident on the surface and the angle of incident is equal. So this angle is our I and this angle is also our I, and this is our source S, angle is given as alpha. And so it will try to bend towards the normal and coming something like this here, as well as it will be moving here in the other direction. Okay. And this is the angle of normal at the other points. Let us call this as A, this is our D, and let us call this as E and this as our B. So for the other end, they will be coming, you can say moving away from normal, something in this direction. So the ray will be traveling like this, and it is given that the angle is same of incident, that I and I, therefore the refractive angle will be also equal. This will be R, so this will be giving us also R, and the emergence angle will be also I for both the rays. And if we draw this line, let us suppose this point is given as O. Well, this is not according to scale, but anyways we will get the feel that the angle will be also coming as alpha, because these two rays will be parallel. These two means our SA will be parallel to our OB. So we can just explain by writing that the divergence angle will remain unchanged, because in case of glass slab, the emergent ray is parallel to the incident ray. We know that the emergent ray is parallel to incident ray for a glass slab. So therefore the divergence angle will remain unchanged, will remain unchanged. Okay. So that will be also equal to alpha. So the option that is given to us, option number B, is the correct one. Option B is correct. So we come to the next question. It was also asked in the year 2000, and it states that a hollow double convex lens is made of very thin transparent material. It can be filled with air or either of two liquids, L1 or L2, having the refractive indexes N1 and N2 respectively, such that N2 is greater than N1 is greater than 1. 1 stands for air. The lens will diverge a parallel beam of light if it is filled with. So we have, you can say, So we have a divergent, okay, so we have a hollow double concave lens. So let us draw a double concave lens, and there are two possibilities. So this is our hollow double concave lens, and there is a possibility that it might be filled with refractive index mu2. So obviously it will be surrounded by the refractive index mu1 as well as refractive index mu1. So inside we are going to have liquid 2, and out on the both sides there will be liquid 1. Now the second possibility is that inside we are having L1 and it is surrounded by L2. So this is our mu1 and this is our mu2 as well as mu2. So inside we are going to have our L1, this is our L2, other side is also L2. And the formula which we can use is our 1 upon f is equal to, we can write this as, let us call this as mu prime and mu double prime minus 1 and 1 upon r1 minus 1 upon our r2. Here mu prime is the refractive index of the lens and mu double prime is the refractive index of medium in which it is dipped. Okay, in order to differentiate from mu1 and mu2, we wrote mu prime as well as mu double prime. So we can see mu prime is our refractive index of lens and mu double prime is refractive index of medium in which lens is dipped. And we want that our the parallel rays should be divergent. So it means incoming should be parallel and the outgoing should be divergent. Okay. So we can say approximately, we will decide the lens later on. So this will be our incoming, and after passing through the lens it should be going like this, diverging. So this is what actually we want, and this entire is basically based on the, you can say, the comparison of the refractive indexes. So we are going to make a comparison between u prime and u double prime. Okay. So in the first case, if our u prime is greater than our u double prime, u prime is greater than, sorry, not u prime but mu prime. So we have mu prime is greater than our mu double prime. So under this condition, the concave lens is going to behave as a divergent and the convex lens is going to behave as a convergent. So you can see under this condition, concave lens behaves as a divergent and convex behaves as a convergent. Now, second condition is that our mu prime is less than our mu double prime. And the nature of the lens is going to be reversed. You can say nature of lens will be reversed. And it is also given that our mu2 is greater than mu1 and is greater than 1. So which basically means that the concave lens will maintain divergent nature if it is filled with L2 and immersed in L1. Immersed in L1. So we can also, you can say, try to solve it mathematically, and let us try to sort it out. We just wrote the formula that 1 upon f is equal to, let me write this as mu prime as well as mu double prime minus 1, and this comes as 1 upon r1 minus 1 upon r2. Okay. And because it is a double concave lens, so you can say that the term 1 upon r1 minus 1 upon r2 is less than 0 for double concave lens. For double concave lens. So for the divergence, we need to analyze the sign of the focal length. You can say that sign of 1 upon f, and we already know that n2 is greater than n1, so therefore our n2, we are given that n2 is greater than n1, so therefore we can write that n2 upon n1 is greater than 1, or this gives us that n2 upon n1 minus 1 is greater than 0. And we just wrote that our 1 upon r1 minus 1 upon r2 will be less than 0. So it basically means that our 1 upon f will be less than 0. Okay. So it means the focal length is negative, so which basically means diverging. So this is only possible that, so you can say that lens will diverge a parallel beam only if we have, you can say, it is filled with more dense optically dense liquid, it is filled with more optically dense liquid, which is obviously our L2, and surrounded by lens dense liquid, that is our L1. Surrounded by less optically dense liquid, that is our L1, because we are given our N2 is greater than N1. So it means it will be lens should be filled by L2 and surrounded by medium L1. And so it will be filled by L2 and immersed in L1, means surrounded by L1. So this will be our correct option, correct figure rather. Yes, option D is correct. Option D is correct. Come to the next question. It was also asked in the year 2000, and it states that in a double slit experiment, instead of taking slits of equal width, one slit is made twice as wide as the other. Then the interference pattern. So we have to find out how the interference pattern is going to behave. At what point there will be maxima and what point will be minima. You see, first one is like intensity of both maximum minima will increase, or maxima will increase, minima will have zero intensity, and C is intensity of maxima decreases, minima increases, and the intensity of maxima decreases and minima has a zero intensity. So it means in the first case it is given that both slits are identical. Okay. So we are given that when both slits are identical, so which basically means they emit light of equally amplitude. Rather we can say they pass the light of equally amplitude. They pass light of equal amplitude. So therefore, because of this equal amplitude, the interference pattern is going to have a maximum intensity and that is, let us suppose, our I max, which will be equal to 4a square if amplitude is given as capital A, and minimum intensity that is our I mean will be equal to 0. Now we come to the given question that one slit is made twice as wide as other. One slit is twice as wide as other. So we assume that the amplitude for the narrower slit is A, then the amplitude of wider slit will be twice because its width is twice. Say amplitude from narrow slit, let us suppose is upper A, therefore the amplitude from wider slit will be 2A because the width is twice. So let us say that slit width of narrow, and for narrow slit let us call this as slit 1, and for wider let us call that slit 2. So let us consider, for the sake of convenience, that our slit 1 is having a width of W, therefore slit 2 is going to have a width of 2W, and we know that the amplitude is directly proportional to the width. Therefore for slit 1 we can say that A1 is directly proportional to W, and for slit 2 our A2 is directly proportional to 2W. So this gives that our A1 will be equal to A, and we get that our A2 will be equal to 2A, which we have already written. Now we can find out the resultant intensity. Resultant intensity. Now we have two amplitudes A and 2A, and the phase difference is, let us suppose, is phi. So we can say that our I will be equal to A1 square plus A2 square plus twice A1 A2 cos of phi, and we substitute the respective values. We get our intensity I will be equal to our A square plus 2A square plus this comes as 2A multiplied by 2A, and we have this cos of phi, and we can easily solve it. This will be giving us A square, we can take as common, so this will be coming as 5 plus 4 cos of phi. Now we know that for maximum and minimum intensity we already know the value of cos of phi. For maximum will be 1, and for minimum it has to be minus 1. So we can say maximum and minimum intensities first is a maximum intensity, which is that our cos of phi is equal to 1. So we can write that our I max will be equal to A square, and this comes as 5 plus 4 giving us 9A square. For minimum intensity we have our cos of phi is equal to minus of 1, and this gives us that I minimum will be equal to this of A square 5 minus 4 is equal to A square. So it means the maxima is more brighter than the equal slit case, because in case of equal slit the maximum intensity was our 4a square. Okay, now it has become 9a square. So obviously it will be more brighter. And for minimum, initially for equal slit it was equal to 0, but now it is non-zero and it is given as a square. Okay. So we can say that the maxima are more brighter than equal slit case. And for minima, we can say the minima are no longer 0. No longer 0. So it means they raise to a non-zero intensity. You can say they are raised to a non-zero intensity. Or we can say there won't be any perfect destructive interference. So based on this, we can say that intensity of maxima is going to increase, and so maxima cannot decrease, and maximum increases, but minima now cannot be equal to 0. So only possible is option number A. Intensity of both maxima and minima increases. So you can say option A is correct. Next question. It was asked also in the year 2000, and it states that a glass plate of refractive index 1.5 is coated with a thin layer of thickness T and refractive index 1.8. Light of wavelength lambda traveling in air is incident normally on the layer. It is partially reflected at the upper and the lower surfaces of the layer, and the two reflected rays interfere. Write the condition for their constructive interference. If lambda is equal to 648 nanometer, obtain the least value of T for which the rays interfere constructively. So we are given that we have, you can say, a glass plate. So we can just draw approximate figure for that. So we have a glass plate which is something like this, and above glass plate of thickness T we have a you can say thin layer is coated. So this we have a thin layer of coat, and let us suppose the refractive index of glass plate is mu2, which is given as 1.5, and for thin layer the refractive index is, let us suppose, is mu1, and that is given as 1.8, and thickness of this coating is given as T, and it is mentioned in the question that the light ray is incident normally on the layer. It is partially reflected at the upper and the lower surface of the layer. So we have, you can say, a light incident which is normal. Let us suppose this is coming into normal into, okay, and partially it is reflected at the upper end and partially it is reflected at the lower end. So we call this as 1 and we call this as 2, and this is our ray. So these are all interrelated with each other, shown separately in order to differentiate with them. Okay. So as we are given that the refractive index of thin film is given as 1.8 and that of glass plate is given as 1.5, and lambda is also given for the second part, and we have to find out what will be our condition for their constructive interference. Okay. Now for the interference, when they are normal, the interference depends upon two things. First will be the phase change upon reflection, and second will be the optical path difference between the two reflected rays. So we can say that interference condition at normal incidence depends upon first is phase change upon reflection, phase change upon reflection, and second it is going to depend on the optical path difference between two reflected rays, between two reflected rays. Now let us try to figure it out, the phase difference, how it is going to behave. So we can say the phase change first is at air and film interface, and the second is at film and glass interface. Okay. And we have to make a comparison between their refractive indexes along the way. So in the first we have air film interface, and air is having a lower you can say refractive index, whereas the film is having a higher refractive index. Okay. So basically we can say from here that air to a higher refractive index, because air normally is our 1 and this mu1 is given as 1.8. So because of this there will be a, you can say, phase shift of pi. So this gives us a pi phase shift, or in the wavelength time we can call it a half wavelength. Now we come to the film and glass interface. Film glass interface, and basically our film is our higher index and our glass is our lower index. Okay, so we can say from film to a lower index, film to lower index. Okay, because film is our mu1 is greater than our mu2, if I have written correctly. Yeah, mu1 is greater than, and here we know that our air is 1, so 1 is less than our mu1. So because of this, there will be no phase shift. No phase shift. So let us now figure it out, the path difference. And we are given, so we have now path difference and we are given that AB is partially reflected as ray 1. AB is partly reflected as ray 1 from the upper surface. From upper surface and partly reflected as ray 2 from the lower. And the refractive lower is refractive index thickness is T and the film refractive index is mu1. So we know thickness is given as T and we have mu1 is our 1.8. So we can write the path difference between the two rays. Path difference between the two rays, that is our delta x, will be equal to 2 mu1 t, and which will be equal to, we can just substitute the value, we get this as 1.8 multiplied by t. This will be coming as 3.6 times t. And also the ray 1 is reflected from the denser medium. Okay, like I said, it is going to give a phase change of pi, and there will be no phase change in the other shift because it is reflected at the rarer medium. Okay. So we can say from here that the phase difference between ray 1 and ray 2, phase difference between ray 1 and ray 2, that is our suppose delta of phi, will be equal to pi. And we need a constructive interference. We need a constructive interference. So we can say for constructive interference, our delta of x should be equal to n minus 1 by 2 and divided by lambda, where this n is our 1, 2, 3 and so on. And delta of x we know is already our 3.6 times t. So we can write this as 3.6 times t is equal to n minus 1 by 2 times lambda. And for the least value of t, which is obviously corresponding for n is equal to 1, you can say for least value of t, our n should be equal to 1. Therefore, we get the t minimum least value T minimum will be equal to lambda divided by, this comes as 2 and this will be 3.6 multiplied by 2, and lambda we already know is our 648 is given to us, and this comes as divided by 7.2, giving us T minimum should be equal to 90 nanometer. Okay. So we found out that least value of T and the condition for the constructive interference. Next question. It was also asked in the year 2000, and it states that a convex lens of focal length 15 cm and a concave mirror of focal length 30 cm are kept with their optic axis PQ and RS parallel but separated in vertical direction by 0.6 cm as shown. The distance between the lens and the mirror is 30 cm. An upright object AB of height 1.2 cm is placed on the optic axis of PQ. Okay. Optic axis PQ of the lens at a distance 20 cm from the lens. If A prime B prime is the image after reflection from the lens and the reflection from the mirror, find the distance of A prime B prime from the pole of the mirror and obtain its magnification. Also locate positions of A prime and B prime with respect to the optic axis RS. So in this case, we are given that we have a two, you can say one is our convex lens and another one is concave mirror, and the difference is that they are misaligned with respect to their axis, and the distance between the two axes, difference between two axes is 0.6. So our PQ is PQ is our axis of our lens and RS is the axis of the mirror, and we have to find out that the distance of the image, and image is represented as A prime B prime, and we also need to find out the location of A prime as well as B prime with respect to the optic axis of our RS. So in this case, we have a concave lens as well as concave mirror. So we are going to start with our concave lens and then we are going to move towards the concave mirror. So we start with the concave lens. And the object distance let us suppose it is given as U lens, which is our 20 centimeter, and we are given the focal length of the lens, let us call that F lens, and that is given as 15 centimeter. So this will be minus 15 centimeter. So we can easily find out the position of the image. So we can use the formula directly, which is our 1 upon F lens is equal to V lens, that is the position of the image, minus 1 upon U lens, that is our object. So from here we get that 1 upon V lens is equal to, we get this as minus 1 upon 15 plus 1 upon 20. So this gives us that the V lens is equal to minus 60 centimeter. So this is the position of the, you can say, image after the lens. Okay. So it means, as it said that it is a negative, so the image will be formed on the, you can say, left of the lens. So from here we can see that negative sign indicates image is formed on left of lens. Left of lens means towards the mirror, and it is 60 centimeter, so obviously it will be forming beyond the mirror. So we can just approximate, draw it with respect to lens. So we are given this is our lens, optic axis, the object is somewhere here, and it is given as AB. Yeah, so this is our A and this is our B, and the image that will be formed if only alone lens is there, it will be something like this, and this will be our image with respect to lens only. Okay. And the distance between this is given coming as our 60 centimeter. So this is our B prime and this is A prime. Obviously it will be magnified, but we get the approximate idea, the position of the image. We can also find out the magnification. You can say magnification of the lens which is our M, let us call that M lens, and it will be coming as V lens upon U lens, giving us minus 60 divided by 20, this will be minus of 3. So obviously from here also we can see that the image formed will be inverted. So we can say negative sign indicate that image formed is inverted, and magnified by a factor of 3, and magnified by a factor of 3. Now we are going to consider our, you can say, the concave mirror. Concave mirror, and so object for the mirror will be the image formed by the lens. So you can say that the object for the mirror will be image formed by lens. Image formed by the lens. So therefore we can write that the object distance for the mirror object distance for the mirror, let us call that as u mirror, will be equal to, this will be over minus 60 and plus 30, which will be giving us minus 30 centimeters. Okay. So, and the focal length of the mirror is also given to us as focal length for the mirror that is our f mirror is also given as 30 centimeter. Okay. So now we can find out the distance of the image for the mirror, and here we can also see that the object distance for the mirror is at 30 centimeter and its focal length is also given as 30 centimeter. Okay. So the object for the mirror will be coinciding with the focal length of the mirror. Now we can find out the, you can say, the image distance. So we can say that our image distance for the mirror same formula we can use, 1 upon f mirror is equal to 1 upon v mirror plus 1 upon u mirror. So we need from here 1 upon v mirror object image distance, which will be equal to, we get this as 1 upon 30, and okay, 1 second, here it should be minus, and this comes as plus 1 upon 30. So this gives us that our v mirror will be equal to 15 centimeters from the pole of the mirror, from pole of the mirror. Okay. And this is our image A prime B prime. Okay. Let me correct it myself. This is not A prime B prime. Okay. Let me draw this as A double prime and B double prime. Okay. And 15 centimeter of pole of the mirror, and we can just find out the magnification also. So we can say magnification of the mirror that is our M mirror will be equal to minus V mirror divided by U mirror. We substitute the values, we get magnification of the mirror will be equal to minus 15 upon minus of 30, and this gives us minus of 0.5, and means the image formed will be magnified by a factor of 0.5. Okay, and this is because of the mirror. Now we can find out the net magnification. Net magnification, and let us suppose that is given as M, which will be equal to magnification because of the lens multiplied by magnification because of the mirror. So we substitute the values, M will be equal to, we get this as, sorry, it has to be plus because this goes away, and we get this as m length was our minus of 3, and this comes as 0.5, giving us minus 1.5. And from here that we can say, as the m is coming as positive, so therefore the image that will be formed by the mirror independently will be upright. Okay. So image will be upright, and this is only when the mirror is individually forming the image, but the combined we can easily see that if there is a negative 1.5. Okay. And therefore this is a magnification, and therefore we can write that the size of the image, which is our a prime b prime, will be equal to minus 1.5 multiplied by the size of the 1.2. This covers minus 1.8, and this will be centimeters. 1 second. (1.2), yeah, this looks good. 1.2, and we have this as 1 second. So this gives us that of image is our 1.8 with a negative sign. So it means the final image that will be formed by the entire combination of lens as well as mirror will be the inverted one. You can see from here that negative sign indicates the image is inverted. The image is inverted. Okay. Now we have to find out the location of A prime and B prime with respect to the optic axis RS. Okay. So we need to find out the A prime B prime with respect to the optic axis. A prime and B prime with respect to optic axis. And optic axis of the mirror. And we know that our the image of B is formed by the convex lens that is 0.6 centimeter above RS, because it is an inverted one. We can write that we are talking about individual points now, A prime, B prime, A, B. Okay, so we can say that image of B formed by convex lens is 0.6 centimeter above RS, because it forms an inverted image along PQ. It forms inverted image. And this image gets magnified 0.5 times by the mirror. Okay. So you can say that this image means B image. You can say this image of B is magnified magnified 0.5 times. So this results in the displacement of the image. So we can say thus the image of B gets displaced by and we can just calculate it 0.6 multiplied by 0.5. 0.6 multiplied by 0.5, this gives us 0.3 centimeter up from RS, from our RS. So therefore, we can find out now the distance. So it means that rest of image lies, this is 1.8 because shift is our 0.3, so this gives us 1.5 centimeter from RS. Thus our A prime will be 1.5 centimeter from RS. And the magnification of the mirror is half, and therefore this will be giving us that point B will be our 0.3 centimeter above RS and point A will be 1.5 centimeter below RS. So we can say that the magnification, okay, we already found out, there is no need to write it. Okay. So point B, image of B means B prime. Okay. So we have this as our B prime. So we can say our B prime is 0.3 centimeter above RS and A prime is our 1.5 centimeter below RS. A prime is 1.5 centimeter below RS. I think these are the only things which we are required to find out. Yeah. So we come to the next question. It was asked in the year 2001 and it states that a ray of light passes through 4 transparent media of refracting index mu1, mu2, mu3, mu4 as in figure. The surfaces of all media are parallel. If the emergent ray CD is parallel to incident ray AB, we must have. So we have to find out the relationship between the refractive indices. And the important part is that the you can say the incident ray AB and the emergent ray CD are parallel with each other. So therefore, let us define all the interfaces point. And let me draw this figure separately. So this is your first surface, this is our second and third, and we got the fourth one. So this is our incident ray, and incident ray, this will be our normal. Let us call this point as P. This angle is our I1, and this way normal, and this way for the normal, and finally it says it is moving in this direction, that is parallel to our incident one. So this is I1, let us call this as our R1. So this will be also our R1, and let us call this as R2. This angle will be also our R2, and this, because of parallelly, we are going to, let us call this as our also our I1. This is P, this is Q, and this we have R. Refractive index are mu1, mu2, mu3, and mu4. So we are going to use Snell's law at each interface, or we can say at each point. We can say at P, we can write, we can write this as sine of I1 upon sine of R2 is equal to mu2 by mu1, and similarly we can use for Q, and Q will be giving us incident sine of R1 sine of R2 will be equal to mu3 by mu2, and R, this will be giving us mu3, sorry, this will be giving us sine of R2 and sine of I1, which will be equal to mu4 and mu3. This is equation 1, 2, and 3. So if you multiply equation 1, 2, and 3, you can say from equation 1, 2, and 3, we get this as sine of I upon sine of R1, sine of R1 upon sine of R2, and sine of R2 upon sine of I1. Is equal to, on the right side, we get this as mu2 upon mu1, mu3 upon mu2, and here we have mu4 upon mu3. So from the left, we can easily see that this entire will be equal to 1, and from the right, we will be left only mu4 upon mu1. Mu4 upon mu1. So this gives us that the mu1 is equal to mu4. So the option number D is the correct one. Option D is correct. Okay, next question. It was also asked the year 2001, and it here states that two beams of light have intensity I1 and 4I interface to produce a fringe pattern on the screen. The phase difference between the beams is pi by 2 at point A and pi at point B. Then the difference between the resultant intensities at A and B are. So we have to find out that what will be the resultant intensities at when the phase difference is at A is pi by 2 and B is pi. So let us assume that there are two beams. So let us consider the first beam. And the first beam, the intensity is our I1, which is given as I, and we have the second beam if it is given as our I2, then this I2 is our 4 times I. And we are given a phase difference at point A. So we can say phase difference at A is our pi by 2 and phase difference at B is given as pi. And we have supposed to find out what will be the difference between the resultant intensity at A and B. So we know the standard formula for resultant intensity, that is our IR. IR will be equal to I1 plus I2 plus 2 square root of I1 I2, and we have this cos of phi. So we can divide this formula into two, first as well as for second. Okay. Therefore, we can write that for IA, for we can say A, we can write this as IA will be equal to I1 plus I2 plus 2 square root of I1 I2 and cos of phi. So this will be I1A, I2A, I1A and cos of phi A. We substitute the values, we get this as I plus 4I, and we have there square root of 2I multiplied by 4I, and the cos of phi A is given as pi by 2. So we get our intensity IA, cos pi by 2 will be equal to 0. So we get intensity of IA is our 5 times I. Similarly, we can do it for our IB. So we can write our IB will be equal to I1B plus I2B plus twice I1A, B and B, and we have a cos of phi B. We substitute the value and difference is given as pi. So this comes as I plus 4I, cos of pi is minus 1, so this comes as 2, and here I have I, 4I and multiply by minus of 1. So this gives me IB will be equal to 1. And we need to find out the difference. Difference. So we can write that our difference, that our delta I will be equal to our delta I is equal to IA minus IB. We substitute the value, we get this 5I minus I will be giving us a 4I. And we can just draw an approximate figure for that. We have two sources. Let us suppose this is our S1 and this is our S2, and this is our screen. So one will be having a phase difference of pi and the other one is having a phase difference of pi by 2. Pi or 2 pi? It was pi. And this you can say second. So we have 2 points. This is, let us suppose, B, and let us suppose this is A. So A is our pi by 2 and B is our pi. So this is approximate figure which can write it out. Next question, and it says that we have in a Young's double slit experiment, 12 fringes are observed to be formed in a certain segment of screen when light of wavelength 600 nanometer is used. If the wavelength of light is changed to 400 nanometer, number of fringes observed in the same segment of the screen is given by. So here we have to find out how the number of fringes is going to change if we are going to change the wavelength. And we have given that for 600 nanometer, number of fringes observed is 12. So we can say that first case, number of fringes, let us put that as n1 is our 12, and the corresponding to that the wavelength is our lambda 1, and this is our 600 nanometer. And for second case, we are only given as lambda 2, and that is our 400 nanometer. In this case, we are going to find out the respective number of fringes within the same segment. And we know that the formula for nth fringe, you can say the position of nth fringe, rather the position of nth fringe, that is our y of n, is given as n lambda capital D divided by small d. Okay. So here small d is the distance slit separation and capital D is the distance between the screen. So we can say for a given segment, means yn will be same for both. So we can say for given segment, number of fringes, that is n, number of fringes is proportional to 1 upon lambda. So we can use this particular equation and we can say this n is proportional to 1 upon lambda, and using for both the cases we can say that our n1 lambda 1 is equal to our n2 lambda 2. We need to find out our n2, so we can say that our n2 will be equal to n1 lambda 1 divided by lambda 2. So we get our n2, n1 is our 12, lambda 1 is our 600 nanometer, and lambda 2 is our 400 nanometer. So this gives us that n2 will be equal to 18. Okay, in both the cases this yn will be same. Okay, next question. It was asked in the year 2001 and it states that the refractive indices of the crown glass for the blue and red light are 1.5, 1.51 and 1.49 respectively, and those of flint glass are 1.77 and 1.73 respectively. An isolated prism of angle 6 degree is made of crown glass. A beam of white light is incident at a small angle on the prism. The other flint glass isolated prism is combined with the crown glass prism such that there is no deviation of the incident light. So based on this, we have to find out two things. Determine the angle of the flint glass prism, and part B is calculate the net dispersion of the combined glass. So here we are given that we are using two lights, blue and red, and the refractive indexes for each is given for crown as well as for the flint glass. Okay. So we can just draw an approximate figure and you can say that if this is our crown glass and the other one is a flint prism, And here we are given a white light. So suppose this is an incident ray light path, and here it will be into two, you can say broadly in two, and this is first one and this is second one. So here also it will bend like this. Sorry. So it will be bending like this, and the middle one is our yellow, and it will be giving like this. So this will be our delta. Okay, because it says there is no deviation in the incident light, and we have to find out the net dispersion. Okay. Angle of the flint glass is to required. Okay, so we have this as a crown glass. Let us suppose this angle is given as A, and this is our flint glass. And this is our angle. Let us suppose we call this as C. So we are given that at a small angle of the prism, so we already know that for delta, if delta is our angle of deviation, for angle of deviation delta, we can write the formula that delta is equal to mu minus 1 multiplied by A. Okay, and this is for small angle approximation. Small angle approximation. And we know that for two prisms which are crown glass and flint glass, we can easily see that so we have for two prisms which is made of a crown and flint glass. And we want that no deviation is there, so we can say the deviation, net deviation is 0. So net deviation is our 0. Okay, so it means the deviation because of the crown plus deviation because of the flint should be equal to 0. You can see deviation by crown glass plus deviation by flint glass should be equal to 0. And let us change it, it doesn't look C. So let us call this as A1 and this angle as A2. You can say that our A1 is given as 6 degree and our A2 is our angle of flint glass. Angle of flint glass. So we have to find out the average index, refractive index of both glasses, flint as well as crown. So you can say mu1, which is our average refractive index, for ground glass, which will be equal to the average of their refractive index for red and as well as violet. So this comes as 1.51 plus 1.49 divided by 2, giving us 1.5. Similarly, we can write that by mu2, which is for flint glass. This will be coming as 1.77 plus 1.73 divided by 2. This gives us 1.75. Now net deviation is 0. Net deviation is 0. So we can write from here that our mu1 minus 1 a1 plus mu2 minus 1 a2 is equal to 0. We substitute the respective values. We get this as 1.5 minus 1 into 6 degree plus 1.75 minus 1, that is our a2 is equal to 0. And this gives us that our a2 will be coming as minus 4 degree. Our negative only states that it must be placed inverted as compared to our crown glass. So you can say negative sign indicates flint glass is placed inverted to crown glass. This you will need the difference. We are really interested in magnitude, so we found out the angle, and next we have to find out the net dispersion. So we have now this is part B, and we are interested in net dispersion. Dispersion is actually the difference in deviation between the blue and the red light. Okay. Dispersion is difference in deviation between blue and red light. Therefore, and formula is quite standard, that is delta will be equal to refractive index of mu, refractive of red, and multiply by A. Now we have two glasses, so we divide this formula into two parts, crown as well as flint. So you can say for crown, we can write this as 1.51 minus 1.49 multiplied by 6. This comes as 0.12 degree. And for flint, this comes as 1.77 minus 1.73 and multiply by 4, and this is a minus of 4 rather, and this comes as minus 0.116. Okay. So net dispersion that is our 0.12 minus 0.16 will be equal to minus 0.04 degree. So it means you can say it is a negative, so the net dispersion red bends red more as compared to blue, and that is reversed as compared to the crown glass. So this was. Go to the next question. And here it was asked in the year 2001, and it states that a thin bioconvex lens of refractive index 3/2 is placed on a horizontal plane mirror as shown in figure. The space between the lens and the mirror is then filled with the water of refractive index 4/3. It is found that the point object is 15 cm. When a point object is placed 15 cm above the lens on its principal axis, the object coincides with its own image. On repeating another liquid, the object and the image again coincide at a distance of 25 cm from the lens. Calculate the refractive index of the liquid. So here we are given two different liquids. One refractive index we know and another one we don't know. And in both the cases, the object and image coincide with each other but at a different distance. Okay. So let's divide the question into two parts so we can approximate the figures. So this is our glass, and above it we have a mirror lens, like this. And when the liquid that is filled here, we know its refractive index, and it is given that the object and the image, they coincide with each other. So this will be our object as well as this will be our image, and in the first case it is given as 15 centimeters. So coinciding means that the incident ray and the reflected ray will be traveling along same path like this, and similarly for the other part also. Whereas for the second, you can say where the refractive index is not known and the distance between the object coinciding and the image is about 25. So in this case also, this is our, let us suppose, object is lying here, and similarly and here also object and image coincide with each other, but now the distance is 25 centimeters. Okay, the liquid is unknown, refractive index, and here the refractive index of the liquid is 4/3. Okay, so this we are given to here as 4/3. So basically we have a convex lens on a plane mirror, so there will be a combination. This entire system is going to behave as a mirror plus lens system in both the cases. You can say a convex lens on a plane mirror so it will be going to behave as a mirror lens system. And the important thing is that the object and image coincide with each other, so therefore the effective focal length will be equal to the object distance. So we are given that object coincide with image Therefore, you can say the effective focal length f, effective focal length if given as f, that will be equal to objective distance, and this is true for both the cases. Object distance. So we have, you can say, now this entire, you can say, mirror lens system, it can be treated as a combination of two lenses. So you can say combination of two lenses. In the first one, we are going to have a glass convex lens, and in the second case, we are going to have a liquid plano concave lens, because liquid is between lens and the mirror. Liquid plano concave lens. Okay. And this is true for both cases. For both cases. So this is our case 1 and this is our case 2. So let us start with case 1. And case 1, we are given that water is having a refractive index of 4/3. Water is present and the refractive index is given as 4/3. So we can find out the focal length of, you can say, glass lens. Focal length of glass lens, that will be 1 upon Fg will be equal to mu g minus 1 upon R1 minus 1 upon R2. As it is equiconvex, R1 for one side will be positive and other side will be negative. So you can say for equiconvex, R1 will be a plus R and R2 will be our minus R. So we substitute it, we get 1 upon Fg is equal to 4/3 minus 1, and this is 1 upon R plus 1 upon R. This is G. This gives us that our Fg will be equal to R. Now we come to the water plano concave lens. Focal length of water plano concave lens. And we can write 1 upon F water is equal to refractive index of water minus 1 upon R1 minus 1 upon R2. Now here one end is plane, another one is a concave. So we can say R1 is equal to minus of R and our R2 will be equal to infinity. And for water it is given as 1.33 refractive index. So we get this as 1 upon Fw is equal to 1.33 minus 1, and this comes as our minus 1 upon R. This gives us 1 upon Fw is equal to minus 0.33 times R. Now we can find out the combined focal length of both combination. So you can say combined focal length, which is 1 upon F is equal to 1 upon Fg plus 1 upon Fw. We substitute it, we get this as 1 upon R minus 0.33 R. This gives us 0.67 R. And we know that our first case, our F is 15 centimeter because the object and image coincide with each other. So we say, but F is equal to 15 centimeter. So we can write that our 0.67 divided by R is equal to 1 upon 15. This gives us that R will be equal to close to 10.07 centimeters. Now we come to the case 2 where the liquid is unknown. Case 2, unknown liquid. Rest of the system will be same. The only thing that is going to change is the liquid, and its refractive index is, let us suppose, taken as mu. So we can write 1 upon, you can say, for liquid lens, we can write 1 upon Fl is equal to mu minus 1, and this comes minus 1 upon R. So this comes as minus mu minus 1 upon R. And for combined, because only thing that is going to change is for the liquid lens because its refractive index is different. For the other part, that is for our what was that? This glass, it will be remaining same. And we can write combined focal length with glass lens. We get this as, let us suppose this is given as F prime. So we can write our 1 upon F prime will be equal to 1 upon R, that was specifically for glass lens, and minus mu minus 1 divided by R. And this gives us this gives us 2 minus mu upon R, and F prime we know is our 25 centimeter. F prime is 25 centimeter, and R we also found out, our R was 10.05 centimeter. So we can write that our 2 minus mu upon 10.05 is equal to 1 upon 25, and this gives us that our mu will be approximately equal to 1.598. So this was the refractive index for the liquid for the second case. Next question. It was asked in the year 2001, and it states that A vessel ABCD of 10 cm width has two slits S1 and S2 sealed with identical glass plates of equal thickness. The distance between the slits is 0.8 mm. POQ is the line perpendicular to the plane AB and passing through O. The middle point S1 and S2. A monochromatic light source is kept at S 40 cm below P and 2 m from the vessel to illuminate the slit as shown in the figure alongside. Calculate the position of the central bright fringe on the other wall CD with respect to the line OQ. Now a liquid is poured into the vessel and filled up to OQ. The central bright fringe is found to be at Q. Calculate the refractive index of the liquid. So this entire question is basically based on two parts. So this is a basic figure. A source is kept at S below 40 cm below point P and 2 m from the slits. In the first case, there is no liquid in this A, B, C, D container, and then the liquid is filled up to this OQ. Okay. So we can approximately draw the figure for, you can say, both the cases. So in the first case, we have two slits. And suppose this is our container, small one, and the middle point. So this is our Q, O, and we have an object, a source rather, that is somewhere here at point S. And this is our point P. It is given that this is our 40 cm. And when this source, this is our S1 and this is our S2. S1 and S2. So let us suppose they meet somewhere here. And we can just join it, and this one also. So let us call this as, this was our A, B, C and D. Okay, let us call this as X, and it is at a height of Y from the middle line, that is our our OQ. Okay. And we can just draw, we can say, a straight line which is joining the point X with this. So let us suppose this angle is our alpha and this angle is our theta. Next case, we have this is filled with the liquid. So we are going to just draw the liquid portion. So this is our central one, and liquid is filled up till this, and source is still here, that is our S, and it says that it meet at point Q. So we can just draw an approximate, so it will be bending in this direction, and this might bend slightly. Okay. So in this way we are going to get, and let us suppose if we join this part, this angle will be still our alpha. Everything that is going to change will be on the liquid side. So these are the figures for case 1 and case 2. So this is our case 1 and this is our case 2. So we can, mainly everything we can solve by using the path difference. So let us solve by path difference before the slits and path difference after slits. You can say path difference before slits, and we can write this as our SS1 minus SS2, that will be equal to D sine of alpha. Okay, so path difference, this will be over after and this will be over before. And similarly, path difference after slits, we can write that our S2A minus S1A will be equal to d sine of theta. And like it said that for small angle, you can write for small angles our sine of alpha will be approximately equal to tangent of alpha, and sine of theta will be approximately equal to tangent of theta. And we want that this x should be our maxima, central maxima. So you can say, one second, meet at x or the meet at? Okay, we can call it x. So we want that for x to be central maxima, this d sine of, d sine, then we can write tan. So we can say d sine of alpha should be equal to d sine of theta, or we can say tangent of alpha is equal to tangent of theta. So we can easily find out the tangents. So tangent of alpha will be giving us 40 by 200, and tangent of theta will be giving us y upon 10. Okay, so this is y. So we can say from here that our y will be equal to 2 centimeters. Now we come to the second part where the liquid is filled with the vessel is filled with liquid, and that will be resulting in the path difference. Case 2, vessel is filled with liquid. So we can say that the path difference at Q after slits let us suppose that is our delta x will be equal to mu minus 1 multiplied by t. T is given as 10, so this becomes mu minus 1 multiplied by 10. And at Q, we can write that d sine of alpha will be equal to mu minus 1 multiplied by 10. Or we can just write it as d tangent of alpha will be equal to mu minus 1 and multiply by 10. So we substitute the values, we get this as 0.8 divided by 10 into 40 divided by 200, and mu minus 1 into 100. Only unknown thing here is mu. We can easily calculate it, that our mu will be approximately 1.0016. So this is the refractive index of the water. Okay. And here I missed to upload one question was there about the refractive indexes, and let me draw that particular figure and try to solve it. It was consisting of three you can say prisms, and we have to find out, and it says that they are traveling. It was asked whether there will be deviation or no deviation option were there, some kind of that. And the figure is given like this. So we have three prisms. So this is first prism, that is our P, and this is our second prism, that is our Q, and this is our third prism. So we have prism P, and we have prism Q, and we have prism R. So we have incident light, and we are given different refractive indexes. So we are given mu1, we are given mu2, as well as we are given mu3. But all these refractive indexes are equal, and therefore the ray inside the prism will be traveling along a straight line, and finally it is going to bend in this direction. And the option is whether it is will be having a deviation, same deviation, and something like that options were there. And so we were mentioned in the question that these prisms have same characteristics, okay. So it means they have same shape, size, and refractive index. So we are mainly interested in refractive index. So we can say mu1 A is equal to mu2 A is equal to mu3, that is suppose equal to mu. And we have to find out the deviation in the prism. Deviation in prism. Now here internally there is all the refractive index are same, so it will be basically traveling in a straight line, okay. And the deviation will be occurring only, let us suppose this is our AB, and we call this as DE. Okay, so whatever deviation is going to take place, it is going to happen only at the two phases, incident phase and emergence phase. Okay, rest it will be same, it's not going to change. And for that we can individually consider phase AB as well as phase DE. And we also know that for deviation delta, we can write delta is equal to I plus E minus A. Okay, and this formula is applicable or drawn with respect to a single prism, but applicable to the combination also. So this is our angle of incident, and this is our angle of emergence, and this is our deviation, and angle is given as A. And we know that, okay, and another thing, another formula we can write, that suppose this is our R1 and this is our R2, then summation of R1 plus R2 is equal to A. And for minimum deviation, that is our delta minimum, our emergence incident angle is equal to emergent angle, and our angle of refraction is equal to A by 2. So these are the two conditions for minimum deviation. Okay. Now we can draw for respective phases. So first phase is our AB. So this is our AB, and we have ray of light that it is too steep. This is our face AB, and we have incident light normal, and this will be our angle of incident. Okay, and at this particular face, if it bends in this direction, so we are going to add, this will be our R1 and this will be angle of deviation. And from the geometry we can clearly see that this angle will be entirely equal to our angle of incidence. Therefore we can write, let us put this as our I1 and I1. So from here we can write our I1 is equal to R1 plus delta 1. And for the other face, which is our DE, we have a ray which is coming something like this, and it is going to bend in that direction. So let us suppose this is our R2, and this is angle of emergence, and this will be our deviation. Let us suppose that is our delta 2. And from here we can write that angle of emergence, because this is R2, this will be also our R2. So angle of emergence will be equal to our R2 plus delta 2. And we already know that for minimum deviation our I1 is equal to E. So we can say for delta minimum I1 is equal to E. Therefore we can write that our R1 plus delta 1 is equal to R2 plus delta 2. Okay. And both R1 and R2 are also equal to A by 2 from here. So we can say this is R1 is equal to R2 is equal to R, which is equal to A by 2. Therefore this R1 and R1 cancels out, giving us that deviation at the incident will be equal to deviation at the emergence. Okay, so we can say they are going to have same deviation. So this option will be correct. One of the options will be there was no deviation, but deviation is there, but it will be same. So this completes all the questions of, you can say, 2007, 2000 there were 7 questions, and for 2001 there were also 7 questions. So this complete all the 14 questions. Thank you.